Integration is a very useful tool, including in the field of biology. We are going to look at how integration is used in neurons. But first, a quick overview on what neurons are. Throughout the nervous system, there are nerve cells called neurons. Neurons transmit information to the brain for processing, and then back to your body cells for motor output. They are able to send the information through electric impulses generated by the changes in their membrane potential. Membrane potential is able to change due to the ions that can enter or leave the nerve cell by facilitated diffusion through ion channels. Over the past century, different equations have been created to model the membrane potential changes inside of a neuron. The leaky integrate and fire is one of the first equations developed that is still used today. Tm is a constant that represents the time it takes for the ions to pass through the membrane. dV over dt is the rate of membrane potential change per millisecond. V of t is the membrane potential in reference to time. R is the membrane resistance. And I of t is the current in reference to time. Here we can use the equation to solve a problem. A neuron has a membrane resistance of 1 milliohm, and it takes 0.85 milliseconds for ions to pass through the membrane. There is a constant input current of 35 milliamperes, and at 2 milliseconds, the membrane potential was 25 millivolts. What was the initial membrane potential? We need to integrate this equation so that we can get V of t. So first, you substitute in the given variables. Then you do separable integration, where you separate the equation based on their terms and then integrate both sides. Then you solve for V of t and you get V of t equals to 35 minus a e to the negative t over 0.85. The next step is to solve for the constant a, which you can do from the information provided that the membrane potential at 2 milliseconds was 25 millivolts. After subbing in the values and solving, you get A equals to 105.16. Finally, we can solve for the initial membrane potential. After subbing in A equals 105.16 and T equals 0, we find that the initial membrane potential was negative 70.16 millivolts. The negative just means that the potential difference in the inside of the cell is less than the outside. So our final answer is that the initial membrane potential was negative 70.16 millivolts, which is approximately the typical membrane potential of a neuron at rest. However, using this equation to solve for membrane potential is limited. This is because in reality, when a neuron reaches action potential, the membrane potential decreases back to resting potential, meaning this equation is constantly repeating itself. So the integration of this equation becomes most useful when used with graphing applications or with coding so that the impulses can be modeled for a particular nerve cell. The equation can be graphed even more accurately when the function of the current is known. As knowledge of neurons grew over the years, scientists were able to improve upon the membrane potential equations. But the leaky integrate and fire equation will forever remain as the foundation.